The last topic I want to discuss in differential equations and transforms is Laplace transforms. Laplace transforms a function of time into a function of complex frequency. And it's very important and useful, especially for solving non-homogeneous differential equations, because sometimes you can convert them into relatively simple algebraic equations which can be solved. The definition of the Laplace transform is given in the extract here from the reference handbook, and here are the definitions again. So f of s, the Laplace transform, is the integral from 0 to infinity of f of t e to the minus st dt, and the inverse transformation f of t, 1 over 2 pi j, integral from sigma minus jw to sigma plus jw of f of s e to the st, where again j is the square root of minus 1 in that transformation. But again, normally most of these can be looked up in tables such as those given in the reference handbook. For example, the Fourier transform of a delta function or an impulse is at the origin at t equals 0 is equal to 1. The Fourier transform of a step function, which looks like this, at t equals 0 is equal to 1 over s. The Fourier transform of a ramp function starting at time 0 is equal to 1 over s squared, etc. And a couple of other things then from this. First, the step function is 1 over s. And if the function is transformed or shifted in time by an amount tau, then the Fourier transform of that function is given by e to the minus tau s multiplied by the Laplace function, which is the last equation right here. So to see how we use that, let's compute the Laplace transform of the ramp function f of t is equal to 2t. Which of these is it? Well, this is one of the standard Laplace transforms in the previous table, and we could just look it up right there, but let's compute it from first principles. So the function here is just a linear function, a ramp function like this, function of t versus t, and we utilize our basic definition of the Laplace transform, which is f of s is equal to integral from 0 to infinity times the function of the given function multiplied by e to the minus st dt. So in this case, the function of t here, f of t, is 2t, so the integral becomes 2t e to the minus st dt, and now the question is just to evaluate that integral. So the factor 2 is constant, I can take that out, and the integral here I might recognize is a standard integral which I obtained from the previous tables we've discussed in the reference handbook. And it appears in the handbook like this. The integral of x e to the ax dx is equal to e to the ax over a squared times ax minus 1. So in this case, we recognize that we replace x by t and a, the exponent here, with minus s. So therefore, the integral becomes e to the minus st over s squared multiplied by st plus 1, with a factor 2 in front. So therefore, the integral is this, evaluated at the limits of 0 and infinity, and substituting in, first of all, t equals infinity, e to the minus infinity is 0, so that term goes out, and the second term, evaluated at t equals 0, that term goes out, leaves me with minus 2 over s squared. So the solution of the integral is equal to 2 over s squared, and the answer is A, which we could have found by just looking it up in the standard tables. Next, we'll do the Laplace transform of a step function of height 1 at t equals 0 and a step function of height 2 at t equals 1 second. Which of these is it? So here's the situation. We have here function of time versus time. So we have a step function of height 1, first of all, at the origin, and then a second step function of height 2, height equal to 2, displaced a horizontal distance of t equals 1 second. What is the Laplace transform of that combined function? Well, here we're going to use two pieces of information from the table. First of all, the transform of a function shifted in time by a time tau, where tau in this case is 1 second, is this expression, is equal to e to the minus tau s multiplied by the Laplace transform of the original function. And furthermore, the transform of a unit step at time t equals 0 is 1 over s, which we obtained from the table. So therefore, the transform of a step of height 2 is 2 times that, and at time tau is equal to 1 is e to the minus s times 1 over s multiplied by 2. So this term, 1 over s, is the Laplace transform of this function, and this term is the Laplace transform of this step function. And finally, we can simply add these together by superposition to find the Laplace transform of the combined function. Therefore, the Laplace transform combined is equal to that, which I can write a little more tidily in that form. Therefore, we see that the answer is A. Now finally, to conclude this topic of mathematics, I'll mention that there are a number of topics that I didn't cover because I think they're of lesser importance in the FE exam, although of course they should be covered in a more comprehensive class. And in particular, we didn't talk about putting linear equations into matrix form and solving by Cramer's rule. We didn't look at a number of topics involving numerical analysis, particularly difference equations, numerical methods, numerical integration, and solving ordinary differential equations by numerical solutions. And finally, we didn't cover centroids and moments of inertia, although I put this in parentheses because those will be covered later on in two topics, topic 6, which is statics, and topics 8, mechanics of materials. We'll talk about those topics in more detail. So this concludes the module on mathematics.